So we're going to talk about a concept called phase in RC circuits. And I don't want you to get perplexerated by it, because phase is actually a concept you're familiar with already. We've talked before about the idea of driving systems at a frequency that suits them. And this is the root of things like why you push people on swings at the point where they're at their maximum, so that you can make their swings bigger. Okay? But it's also, phase is at the root of things like why, when you're walking down the street with someone, you fall into step with them. So you're moving either the same foot or alternate feet at the same time. And that's why some people just can't walk comfortably together, and they're always kind of jiggling against each other. And you probably know people that you just can't walk beside because you can't make your stride in phase. So electricity, weirdly enough, has a similar concept, the concept of phase. And what we're looking at here is the phase relationship between the voltage across the resistor and the voltage across the capacitor in an AC circuit. So our circuit's all set up, it's nice and simple, and what we find is that if we measure the resistance across the voltage and the resistance across the capacitor, this is the relationship we end up with. The resistor starts at 0, gets big, comes down, passes through the equilibrium again, reaches its maximum, comes back up. Nice tidy sine curve. What we find when we measure the voltage across the capacitor is we still get the same sine curve, but it's offset. It's not in phase, okay? When the voltage across the resistor is at 0, the voltage across the capacitor is at its negative equilibrium. And we can follow that sine curve through. And what we find is the period is the same because they're both being driven by the same AC frequency, but the voltage varies across them differently. And so we can draw two what are called phasor diagrams for it. And I hope you'll look at them and recognize something. A reference circle. And so we call this a phasor diagram. And so here's our voltage across the resistor at the equilibrium position. There it is. Okay? At this point in time, there is our voltage across the resistor at 0, passing through the equilibrium. Okay? And it's going to be turning in this direction. If we do the same thing with our capacitor voltage, okay, there it is there, and you'll see I've put it under the equilibrium line a bit better this time. Here's our capacitor, okay? It's at its negative maximum, and it's also turning in this direction. Now, where this gets really interesting is we want to be able to consider the total resistance-like behavior in our circuit, and we want to be able to consider how our supply voltage varies. It's easy for us to measure, or relatively easy for us to measure the resistance, the voltage across the resistor and the voltage across the capacitor. And for reasons that will become clear a little bit later when we start talking about this using resistance and reactance, we're going to put these together. And so what we get is at this position here, okay, at this position here, we have some resistance across the resistor, we have some resistance or some voltage across the capacitor, might be a better way of saying it, and what we get is the supply voltage. Okay, and so this is the supply voltage. So you can see that the voltage across the resistor and the voltage across the capacitor add together as vectors to give us the supply voltage, and the supply voltage is also changing. It's also turning, changing its response, varying according to a sine relationship. So this here enables us to talk about the way that the supply voltage, the resistor voltage, and the capacitor voltage work together, and we can then combine them to talk about a new concept called impedance.